Have you ever picked up a gadget and just thought, how did they even make this? Well, today we're diving into the art of finding that out. We're talking about reverse engineering, the incredible process of working backward. You take something apart, not to break it, but to truly understand its secrets. It's a huge deal in modern manufacturing, so let's get into it.
All right, here's our game plan. We're going to start with a real-world manufacturing crisis that nearly shut a company down. Then we'll see how you can turn a physical thing back into a digital blueprint. We'll get into the huge difference between just copying something and actually understanding it. Then things get crazy when we shrink down to the microscopic level. And finally, we'll see how this whole art of deconstruction is literally rebuilding our future.
So, put yourself in this situation. Imagine you run a factory. Your entire business, your whole production line, depends on one specific little part that you get from someone else. Now, what happens if that part just goes away? What if the original design for it is gone for good?
And look, this isn't just some hypothetical. This actually happened. There was a loudspeaker company that made almost everything themselves, except for one absolutely vital component, the speaker basket. For that, they had one supplier they trusted. Everything was humming along just fine.
And then, boom, their supplier gets bought out by a bigger company. The new owners say, no problem, we can make that part for you. But when the new baskets arrive, they don't fit. They're just a little bit off. And just like that, the entire production line is in serious trouble.
And just when you think it can't get any worse, it does. That new company goes bankrupt. And somewhere in all that corporate chaos, the original, perfect design for that basket, it's just lost, gone. They still have the physical part, but the blueprint to make more vanished.
The result is what you'd expect. Production grinds to a dead stop, an entire business crippled because a single digital file disappeared. So what do? The map is gone, but you're still holding the treasure.
This is where the art of deconstruction comes into play. See, the real point of reverse engineering isn't just about remaking something. It's about recovering lost knowledge, about digging into a finished product to understand all the design choices that are hidden inside.
So here's a textbook definition. Reverse engineering is the process of taking a physical object, measuring every single detail about it, and then using all that data to build a brand new digital blueprint, what we call a CAD, or computer-aided design model. You're basically turning a thing back into an idea.
So how does that actually work? I mean, how do you really go from holding a physical part in your hand to having a perfect working digital design on your screen? Well, let's walk through the steps.
It's kind of like a 6-step dance. First, you identify the product, in our story, the speaker basket. Second, you do your homework. You have to understand not just what it is, but why it is, how it works with everything else. Third, you make a plan. How are you going to take this thing apart and scan it? Step 4 is the dissection, carefully taking it apart and scanning every piece. Fifth, you take all that data and build your digital model. And finally, and this is maybe the most important part, step 6, you build a prototype from your new blueprint and you test it like crazy to make sure it works perfectly.
And what's really cool is how engineers have formalized this into a continuous cycle. It all starts with data capture. Think 3D scanning. Then you process that data, basically cleaning it up. Next, you segment it, telling the computer, okay, this flat bit is a plane, this round bit is a cylinder. From there, you model all those features, stitch them together, and bam, you've got your CAD model ready to go. It's this really elegant loop from the physical world to the digital and back again.
But here's where we get to a really important point. Because, anyone can measure an object and just make a copy. That's not what engineering is all about. The real magic is understanding the why behind the what. And that gets to the very soul of this whole field.
I love this quote from a discussion I saw online. It just nails it, right? It says the difference between real engineering and just slapping stuff together is that an engineer needs to understand why it works the way it does. It's not about recreating a shape. It's about recreating the thought process behind that shape.
So let's break that down. Copying is simple. You measure the geometry, you make a model, you replicate the shape. Done. But true reverse engineering, that goes so much deeper. It's about understanding the original design intent. It means analyzing the materials, testing the performance, and ultimately replicating the function, not just the form. That's the key difference.
Okay, so we've been talking about parts you can actually hold in your hand. But what happens when the part is a super complex maze of circuits that's billions of times smaller? Well, welcome to the microscopic heist.
Yeah, we are now entering the world of semiconductor reverse engineering,
We're talking about computer chips, where the components are so tiny they're measured in nanometers. So how on earth do you deconstruct something you can't even see with a normal microscope?
Well, it takes what you could call digital archaeology, and it requires these incredible collaborations between major research institutes and tech companies. It's this super complex cycle of prepping the chip, imaging it at resolutions that are hard to even imagine, and then some seriously sophisticated analysis. So how do you actually excavate a microchip?
First, you have to peel the onion, layer by atomic layer. Scientists use focused ion beams to shave off unimaginably thin layers of the chip. After they remove each layer, they hit it with a high-powered electron microscope to take a picture. Then, powerful software stitches thousands of those pictures together to create a perfect map of that one layer. Then, they do it again and again, stacking all those maps to build a full 3D model of the circuit. This lets them figure out what it does and even hunt for hidden threats, like malicious hardware trojans.
And the scale here is it's mind-bending. They're analyzing technology that's smaller than 40 nanometers. To put that in perspective for you, a single human hair is about 80,000 nanometers thick. This is reverse engineering at the absolute edge of what is physically possible.
So from a factory floor crisis to a microscopic lab, why does all this matter so much? Why is this process of taking things apart so critical for, well, building our future?
Well, the uses are everywhere. It's huge for quality control, making sure a part coming off the line is a perfect match to its blueprint. It's essential for what's called MRO, maintenance, repair, and overhaul, letting us remake old, obsolete parts for planes, trains, and power plants. Companies use it to analyze what their competitors are doing. It protects patents. And as we just saw with the chips, it's a massive deal for national security, helping to keep our supply chains safe from hidden dangers. So from a simple speaker basket to a circuit that's almost impossibly small, reverse engineering is this incredible power. It lets us recover lost knowledge, secure our technology, and understand our world by deconstructing it piece by piece. But that kind of power brings up a pretty deep question. If we're getting to the point where we can take literally anything apart, what's the one thing we should choose to leave whole?